You're standing in an elevator. The cable snaps. The elevator starts to fall. And during that fall, during that terrifying moment, something happens. Gravity disappears. If you drop your phone, it hangs in the air. You hang in the air. If you push gently in any direction, you drift that way. Like you're in space. Completely weightless. But wait, how is that possible? Earth is still there. Its mass is still there. Gravity should still be there. Einstein says, no, because gravity isn't actually a force. It never was. Newton was wrong. Fundamentally wrong. And once you see this, everything in the universe starts to look different. This is Einstein's most radical, most mind-bending discovery. And most people still don't understand it. First, we need to understand what Newton said. Because for 300 years, everyone believed him. According to Newton, gravity is a force, an invisible pull between two masses. The apple falls because Earth pulls it. The moon stays in orbit because Earth pulls it. Simple, elegant, mathematically perfect. Newton's equations worked. You could calculate planetary motion. You could send rockets to the moon. You could place GPS satellites in orbit. Everything worked exactly as Newton said it would. But here's the problem. Newton explained how gravity worked, but he never explained why it worked. Two masses pull on each other. Okay, but how? There's nothing between them. Empty space. No mechanism. No connection. How does the sun pull on Earth? There's 150 million kilometers of nothing between them. How does it reach across that gap? What does it travel through? Newton's answer, I don't know. But it works. And for 300 years, that was enough. People stopped questioning. Gravity was just a feature of the universe. Something to accept. Then Einstein came along. Part of Einstein's genius was asking questions from different angles. In 1907, he was sitting in an office in Berlin, working at the patent office, and he imagined a thought experiment. A man falling off a roof. What does he feel while falling? Your first instinct, he feels gravity. He feels himself being pulled down. But Einstein noticed something. The falling man is weightless. If he's holding an object and lets it go, the object stays next to him. It doesn't fall to the ground, because they're both falling at the same rate. For the falling man, in that moment, there is no gravity. None. That's strange, because gravity is clearly there. Earth is still there. Its mass is still there. The man is accelerating, moving toward the ground. But the man doesn't feel it. Einstein called this the happiest thought of my life. And it led him to a shocking conclusion. There is no difference between gravity and acceleration. Now let's unpack that. Imagine a rocket ship in space, far from Earth, where there's no gravity. The rocket engines fire, and the ship accelerates at 9.8 meters per second squared. You're inside that ship. Your feet press against the floor. If you drop a ball, it falls to the floor. You feel completely normal. Now a totally different scenario. You're standing on Earth. No rocket, just normal gravity. Your feet press against the floor. If you drop a ball, it falls to the floor. You feel completely normal. Einstein's question, what's the difference between these two experiences? Answer, there is no difference. Being in an accelerating rocket is the same thing as standing in gravity. Physically indistinguishable. But wait, if they're indistinguishable, maybe they're the same thing. Maybe what you call gravity is just acceleration. But acceleration in what? Here's Einstein's leap. Acceleration in space itself. Newton thought space was flat. A flat, fixed, unchanging stage. Objects move on that stage, and forces push and pull them. Einstein said, no, space isn't flat. It's curved, and mass curves space. To visualize this, let's use a metaphor. Imagine a large rubber sheet. Flat, taut, stretched horizontally. Now place a heavy bowling ball in the middle. The sheet sags. The ball creates a dip around it. Now take a small marble and roll it across the edge of the sheet. The marble wants to go in a straight line, but the sheet is curved, so the marble starts curving around the ball. The marble isn't being pulled. The ball isn't pulling it. The marble is trying to go straight, but straight isn't straight anymore. It's curved. That's Einstein's picture of gravity. The sun curves space. Earth moves through that curved space. It wants to go straight, but space is curved, so its path loops around the sun. No pulling force, just geometry. Now, this metaphor is good, but not perfect. Because in the rubber sheet, the bowling ball is pulled down, by gravity. But in space, there's no down. And what curves space isn't gravity. It's mass. Something deeper is happening. Space isn't three-dimensional. It's four-dimensional. Spacetime. And mass doesn't just curve space. It curves time. In fact, most of gravity comes from the curving of time, not space. Here's how. Near mass, time slows down. A clock on top of a mountain runs faster than a clock at the base of the mountain. The difference is tiny, but measurable. And this time difference, as objects move, creates a curved path. Objects move in straight lines through four-dimensional space-time. But those straight lines look curved in three-dimensional space. That's why the apple falls. It's going straight in four-dimensional space-time. But Earth has curved space-time, so the straight path takes the apple to Earth. No force, no pull, just geometry. Now let's return to the falling elevator. The elevator is falling. You're inside it. You're weightless. Newton says, gravity is still there, pulling you down. But the elevator is also being pulled down, so you don't feel it. Einstein says, no, you don't feel gravity because falling is the natural state of motion. You're moving in a straight line through four-dimensional space-time. No force, no acceleration, just following the geometry. When do you feel gravity? When you're deflected from that straight line, standing on the ground, feet on the floor. The ground is pushing you up. That's a force. That's deflecting you from your natural trajectory. For Einstein, standing on the ground is the accelerated state. Free fall is the natural state. This is counterintuitive, but it works mathematically perfectly. And it's not just theoretical. It's testable. Einstein predicted that if space is curved, light should also curve, because light travels in straight lines. But if space is curved, straight lines bend. In 1919, during a solar eclipse, scientists measured light from stars behind the sun was bending by exactly the amount Einstein predicted. Gravity bends light. Newton's theory can't explain that. Einstein's can. Later, scientists measured time. They put atomic clocks on airplanes. One flew high, one stayed on the ground. When they returned, the clocks showed different times. Time runs faster at altitude. Einstein was right. GPS satellites have to correct for this every day. If they didn't correct for relativity, GPS would be off by kilometers. This isn't theory. This is measurable reality. Here's what Einstein discovered. Gravity is not a force. It's the geometry of spacetime. Mass curves spacetime. Objects move in straight lines through that curved spacetime. But straight lines look curved. Newton explained gravity. Einstein explained space. And that difference is enormous. Because if space can curve, what else can happen? Black holes. Places where space is so curved that not even light can escape. Newton's theory didn't predict black holes. Einstein's did. Gravitational waves. Ripples in space-time traveling at light speed. Newton's theory didn't predict this. Einstein's did. And we detected them in 2015. Expanding universe. Space itself is growing. Galaxies are moving apart because the space between them is expanding. Newton's theory can't explain that. Einstein's can. All of this comes from the same fundamental idea. Space isn't just an empty stage. It's a dynamic structure. It can bend, warp, ripple, expand. And we're inside that structure, subject to it, following its geometry. Newton explained what we see. Einstein explained why we see it. But here's the thing. This still isn't the complete story. Einstein's theory works perfectly for big things. Planets, stars, galaxies, black holes. But at very small scales, at the atomic level, another theory takes over. Quantum mechanics. And quantum mechanics and relativity don't speak the same language. Quantum mechanics says space is smooth and continuous. Relativity says space is smooth and curved. When you try to combine them, the math explodes. You get infinities, nonsensical answers. Physicists have been trying to unite these two theories for 100 years. They haven't succeeded yet. So yes, Einstein explained gravity. But a deeper explanation is still out there somewhere, waiting to be found. Maybe space is actually made of something. Maybe at very small scales it's discrete. Maybe gravity is a quantum phenomenon. We don't know. But what we do know, gravity is not what Newton thought it was. It's not a pulling force. It's not a push. It's not an invisible hand. It's geometry, the shape of spacetime, the fabric of the universe. And right now, you're touching that fabric, following that geometry, moving along those curved lines. Gravity isn't pulling you. Space itself is carrying you. And once you see this, everything changes. Standing still becomes an act of effort. Falling becomes natural. And the universe stops being Newton's mechanical machine and becomes Einstein's dynamic fabric. That's why physics is beautiful. It destroys your intuition. It rewrites reality. And it shows you that the universe is stranger, deeper, more elegant than you thought. Gravity is not a force. It never was. And now you know why.